Okay, here we go. Chapter 5. So section 5.1 is just information about what conic sections are. So we just are going to learn here about what they are. So conic sections are literally slices of a cone or set of two cones called a double napped cone. So you can see some illustrations here with a double napped cone and a plane that's intersecting one of the cones straight across. When that happens, with a horizontal plane, we get a circle. If we tilt our plane a little bit so that it's not horizontal, we get what we call an ellipse. Ellipses and circles are very closely related, which you'll learn in sections 5.2 and 5.4 in this chapter. A parabola is sliced through the bottom of the cone and ends up creating a parabola. So it's important to note that the cone goes forever, so I guess it doesn't really have a bottom. But instead of going across the cone, it's going toward the base of the cone. Okay, hyperbola is straight up and down through the two cones. That's where the two cones come into play and would look something like this. So hopefully those illustrations make sense. You're both going to pull up the reading for this section and look at those a little closer. There's some other stuff in the reading about other types of conic sections which are not really all that important to us. But they're interesting. Feel free to read through them. Okay, let's jump in and talk about circles. Hopefully you've learned this before because this is a fairly common topic in several different courses. I can't remember exactly where it fits into Common Core, but I know you get it somewhere. I think it might be secondary too, so it's probably been a couple of years since you've seen this. Okay, so the definition of a circle is that it has a center and a radius. And we call the center HK just because we use H and K for our horizontal and vertical numbers all the time, right? And if I just, oh, it's a little bigger than I expected. So our circle has a center. Oh, when I was drawing it, it was showing me that center. Now it's not. So our center can be on a graph at 0, 0, or it can move to anywhere, HK. And then R, of course, refers to the length of the radius. And a radius, in case you've forgotten, which I'm hoping you haven't, because that's a pretty basic mathematical concept that probably if you're in this class you would know and remember. It's going to be really important in Math 1060 next semester. So here is a radius. So the radius is from the center of the circle to a point on the circle. So we have infinitely many points around a center that are that same distance r from the center. So a circle is the set of all points in the plane whose distance to the center is length r. So that's a consistent length no matter what point you go to on the circle. Okay, the standard equation of a circle actually comes from Pythagorean theorem. I don't know if knowing that helps you maybe understand it a little better. In fact, you know what? I'm going to go back to the circle I drew on the previous screen and show you why Pythagorean theorem applies. So, just in case you've not seen this or didn't remember this before, if I draw a line straight across here, and I draw another line to my point on my circle there, and I draw another line, I should probably change the colors of these a little bit. Just having a hard time remembering how to find different colors for my line drawing tool. Okay, so there's a line there. Let's select this one and make it a different color, like purple or something. Okay, so I can differentiate between lines. So we have the length r to a point on the circle, right? Well, the distance horizontally to get to point r is an x value, right? And the distance vertically to get to this point, I guess it's not point r, it's just a point on the circle, referred to in our definition as xy. So we have a point on the circle right here at x comma y, right? And x, of course, is a horizontal distance, and y, so x would actually just be this length right there. And y is that vertical distance. And together, those two coordinates create our point on the circle at xy, which is a point that's on the circle on our graph. So based on that definition, this point xy is related to the length of x by the length of y by finding the diagonal, which is the hypotenuse. And that, of course, can be done with Pythagorean theorem. So Pythagorean theorem is a squared plus b squared equals c squared, and that's for all right triangles where a and b are legs and c is the hypotenuse. Well, in this case, the legs we're referring to are the x and y values, and the hypotenuse we're referring to is the diagonal, or the distance to the actual circle, which is r. So x squared plus y squared equals r squared. We just use Pythagorean theorem for that circle. Now, that is actually the equation of a circle, but that would be if its center was at 0, 0, and we didn't worry about moving it to another place. Because let's say this is from 0, so this is distance x, and this is distance y from 0. Here's our point with a length of r. So this particular formula is contingent on that center at 0, 0. So if we want to move our equation to a different center, which we need to be aware of, we're going to insert h and k into our formula. So x minus h squared plus y minus k squared equals r squared. We still have that Pythagorean theorem, x squared plus y squared equals r squared, with the added h and k, which gives us the center at hk. Now, of course, if those were 0, 0, they wouldn't even matter. You would just have x squared plus y squared equals r squared. But if it does move, notice how h and k and the numbers in our formula are opposites. Just like we're used to things horizontally being opposite, this time our vertical number is going to be the opposite value as well, just because it's inside that square. And so mathematically, it's the number that we would plug in for y and subtract k from it to get that center value. So it's going to be the opposite number. So radius r and center hk gives us this formula. Okay, let's write an equation of a circle with the center at -2, 3, and radius 5. We're just going to use our formula. So x minus, and our h value is -2, and then y minus, and our k value is 3. Don't forget the squares, because Pythagorean theorem doesn't work without the squares, and then radius squared. Again, another important part of Pythagorean theorem. We should simplify this, make it look a little nicer, so we don't like to have these double negatives. We're going to do x plus 2 squared plus y minus 3 squared, and then instead of 5 squared, just simplify that to 25. That is our standard form for this described circle. Okay, find the center and the radius of the circle described by the equation x plus 2 squared plus y minus 1 squared equals 4. So notice how if this is a plus 2, just like in our previous problem, that gives us an h value of -2. And since this is a -1, that's going to give us a y value of +1. And then 4 is not the radius. 4 is the radius squared. So we have to square root to find the radius. So h is going to be -2, right? So we're going to say our center is at -2, +1. I found that by just taking the number next to x and doing the opposite, the number next to y doing the opposite. And then our radius is simply 2, and we find that because we would take the square root of 4 and get 2, because this is r squared. So to graph this, I'd go -2 up 1, radius 2. I just kind of, to make my circle look better, do some points 2 in all directions, and then sketch that in. the best you can. I don't expect